and 6 minus 6 is 0, and 0 squared is 0. So it appears to have hope, but we are not sure. Hope doesn't mean that the limit exists. It means it has potential. So of course then I will simplify by, first of all, factor the numerator, and I realize that I can get away from, I can simplify, get one of those two factors out of the way. So at this point, the limit is from 2 over x minus 3. But now this is 2 and this is 0. And there is no hope anymore. So when I plug in 3, I get 0, but I cannot plug in 3. I have to plug in 2.9 because 3 from the left is 2.9. And because the denominator is negative and the numerator is positive, the answer is negative infinity, which makes x equals 3 a VA. So the only twist here was that you had to see to simplify, to factor. So the keywords in math are always factor and simplify. There are other keywords, but these are very important keywords. Okay, now any questions for me, please?
When I answered, that's the first thing I did. I plugged it in first.
Yes.
0 over 0, so I said there's hope.
Yes.
And I said it's approaching 3 from the left. And then I plugged in 2.9.
But you have to simplify first. You have to simplify a factor first.
Well, I simplified in mine, but I didn't get the chance before I submitted.
So you have to simplify and you have to get here. And then you realize it's 2 over 0. Right. So this one has no hope. This one does. But hope does not mean that it exists. Keep that in mind.
Mm-hmm.
Okay. So
would you have to simplify? Like I did it without simplifying, if you still got negative infinity, just knowing that 2 times 2.9 minus 6 was going to give me a negative, and 2.9 minus 3 would give me a negative, but then squaring it would make it positive. So couldn't you find it without factoring as well?
When you have initially 0 over 0, you have to go through this step.
Okay.
You cannot conclude that 0 over 0 is negative infinity.
No, I plugged in from there, but I didn't factor and then plug in 2.9. I plugged in 2.9 into the original equation and still got negative infinity.
But we cannot, we cannot plug in. We never do that. We never, ever plugged in 2.9.
I thought you...
We always plug in. We always plug in 3 to see what we have.
Mm-hmm. I did that and got 0 over 0.
Yes, and then we have to simplify it, because 0 over 0 does not mean negative infinity unless it means negative infinity in the next step.
Right. So I did the next step, but I didn't factor before that next step.
But that's the key. That's the key here, because we are trying to eliminate the factor that gives us 0 over 0. That's the idea.
Okay.
So the culprit that creates 0 over 0 is this factor, x minus 3. Mm-hmm. That's the problem. X minus 3 is the problem. So once I have 0 over 0, I know that I have to eliminate at least one x minus 3. Because that is the problem. That's what creates 0 over 0. After I eliminate 1, I realize that there is still 1 left over. And now there is nothing I can do about it. So when I plug in 2.9, I get negative infinity.
But you're saying we can't plug in 2.9?
We don't ever plug in 2.9 in when we get 0 over 0. If you plug in 2.9, you are not going to get 0 over 0.
No, after getting 0 over 0. Like how you're saying we plugged in 2.9 into the denominator of x minus 3. So I plugged in 2.9 into...
So first you got 0 over 0.
Right. Yes.
Okay. And then you have to write limit. Or you're not writing anything.
Right.
So now you're plugging 2.9.
Mm-hmm.
When you plug in 2.9, the numerator becomes negative and the denominator becomes positive, and you eliminate all the rest of the steps and you immediately said negative infinity.
Mm-hmm. Yes.
I guess it's acceptable. I don't recommend it. This is not what we did. I wouldn't say it's completely incorrect. But this is...
Because wouldn't the factored form be equivalent to the non-factored form?
No. 0 over 0 is not 2 over 0. It becomes 2 over 0
Right,
after simplification. So after you simplify, then you get this. And now you apply the 2.9. I'm not saying that this is entirely incorrect, but this looks like calculator work more than showing step by step what it means.
Okay.
Because I can also do this with a calculator, plug it in, so put the function in, and then just approach 3 from the left. I'll get an answer. So I wouldn't say that this is incorrect, but I would say is not complete. It's correct, but this is not what we did. So we're not plugging in 3 and 2.9 in the same situation when we start with 0 over 0.
Okay.
If we start with 2 over 0, then yes. First we plug in 3, and then immediately we plug in 2.9. I would have to agree. But not when we start with 0 over 0. Because you may not get this. By chance, it happened that you got that.
Mm-hmm.
But I don't know. Maybe the limit exists. So I don't recommend this step if you have hope first. If you don't, yeah, of course, I fully recommend it. You're right.
You're saying if we have hope, we should then factor.
Absolutely, and eliminate and then see what happens. Maybe because maybe the answer is 5.
Okay.
You can plug in.
Okay, without having to plug. Okay.
Right. So when you get 0 over 0, stop, think about it, try to simplify, and then, oh, okay, yeah, now I have to plug in 2.9.
Okay. That makes more sense. Thank you.
Thank you. Very good. So now let's talk about the precise definition. So section 2.4 is the only proof. I'm going to make it as simple as possible. We are only going to look at linear functions. Linear functions only. No quadratic, cubic, nothing. Very simple. So the precise definition of the limit, or the epsilon delta definition. Epsilon delta. These are Greek letters, very widely used when it comes to the precise definition of the limit, or epsilon delta definition. There is also a delta that we will see later on. This is the uppercase delta, and this is the lowercase delta. Okay? We're not using the upper. I haven't seen the upper epsilon. Okay, so what is all this? First, I want to teach you a couple of mathematical symbols, very widely used, because they will make the definition much easier to write. We always have to write the definition when we show the precise definition of the limit. So here's one. There exists for every this one for later, in or belongs to I didn't put it here.
Your screen went out.
Yes, yes, I touched the table. I can breathe, I cannot breathe, I cannot touch the table, I cannot do anything. Sorry about that. So, in or belongs to, such that. Okay? Okay, so I'm going to write the definition in plain English first, and then I'm going to write the definition using these symbols. Okay? And then I'm going to explain every little piece of it. It will look gibberish at first. It's very simple, but it will look initially very complicated. So bear with me. So first, a little graph. So here's the function. I promised linear function, so I'm just going to graph a linear function. So this is f of x. This is a. And this is our favorite L. So can anyone help here with a limit? As x approaches a from f of x is?
L.
Of course. I'm going to use a double equivalency symbol. Double equivalency. Symbol. What's the big deal with a double equivalency symbol? It means this. This implies this, whatever I'm going to write here, and what I'm going to write here implies this. So going back and forth. This implies this implies this. And now I'm going to use just plain English, and then I'm going to use these symbols. And then I'm going to explain every piece of it. For every epsilon near, of course, positive, near L, I will find a delta near A such that whenever I pick x near A, f of that x, f of x, will fall within epsilon of L. Who wants to write this every time we use this definition? No one. We're not going to use this. You can. I accept it. It's perfect. First of all, let's identify and analyze what it means before I use those little symbols and the whole definition is in one line, like this, not on 4 rows. So I'm going to go to the next page. I'll come back here because I need a bigger graph to explain what I'm doing. You can say a lot of explanation for one little example. True. I agree. Here's my function again. Here's A. Here's L. Okay, so I need more colors. So for every epsilon near L, when we say small epsilon, positive, small, we mean small, tiny. So this is the limit right here, and this is epsilon, this and this. So this point up here is L plus epsilon. This point down here is L minus epsilon. It's a symmetric interval. L plus epsilon, L minus epsilon. So I repeat. for every epsilon positive near L. L plus, L minus. I will always go to the function and come down. Go to the function and come down. I will always find that it has to be the smallest of the two. This is the smallest in my graph. So this will be the delta near A. So this point is A plus delta. Of course, this point is A minus delta. So for every epsilon positive near L, I will find a delta corresponding. Very important word. Corresponding delta. It depends on epsilon. See, if I have a smaller epsilon, I will have a smaller delta. If I have a bigger epsilon, I'll have a bigger delta. So delta corresponds to this. The next delta corresponds to the next epsilon. If I have 0.1, then this may be 0.3. If I have 0.4, this may be 0.7. I don't know. But delta depends on epsilon. So delta is corresponding to epsilon. For every epsilon near L positive, I will find a delta, of course, also positive, near A, such that, and now such that, when I pick X anywhere between A minus delta and A plus delta, not A, we know X cannot be A. If I pick X, the corresponding f of X will be within epsilon away from the limit. This will be the f of X right here. One more time. For every epsilon, I will find the corresponding delta such that when I pick X close to A, within delta, f of X will be within epsilon away from the limit. Why does this happen? Because the limit exists. And this mechanism works for any epsilon, not just for a particular epsilon. I can have epsilon equals, it cannot be 0, right? It has to, both have to be greater than 0. So for 0.1, I'll determine the corresponding delta. For 0.3, I'll determine the and so on and so forth. This will always happen. For every epsilon, I'll find the corresponding delta such that when I pick X here, or maybe here, or maybe here, not here. Because see, it's outside. If I pick here, it's outside of the interval. If I pick here, it's outside, right? So I have to make sure that I choose the smallest delta, not the bigger delta. So I meant to say here. So if I choose the bigger delta, here will be outside of the interval. So I always have to choose the smallest delta. This mechanism will work. F of X will always be inside. F of X will always be inside. F of X will always be inside the interval. L minus epsilon, L plus epsilon. This works because the limit exists for every epsilon. So now here's how we write the definition with symbols to make it short. It's up to you. You may say, I don't want your symbols. I want to write the whole thing. Go ahead. I will not write it again. So, limit as x approaches a from f of x equals L. Now, distance is always measured with the absolute value. So before I write the definition, I want to clarify something. Distance between x and a is written x minus a in absolute value, less than delta. This is how we write it. The distance between a and x, or x and a, doesn't matter. This distance is written as the absolute value of x minus a less than delta. We will also put in front greater than 0. And you can say, wait a minute, the absolute value is always greater than 0. Yes, but the fact that we write greater than 0, we really mean not equal to 0. In other words, you cannot pick x to be a. That's all it means. Now also the distance, this distance here, the distance between f of x and L is the absolute value of f of x minus L less than epsilon. This is how we write the distance between f of x and L. The absolute value of f of x minus L less than epsilon. Okay, finally, let me stop this